8, we're going to look at ionic bonding. This is going to be a little more in depth about how ionic compounds are formed. Now, the first thing we're going to do, though, is we're going to look at electron transfer using Lewis structures. So, to begin with, I'm going to do the electron structure for magnesium. And then I will do the fluoride. We have 2 fluorides. And remember, fluoride is got 7 valence electrons. So I cheated on the first one because I knew what it looked like. So what's actually going to happen is the electrons from magnesium are going to be transferred. So the magnesium will end up being a 2+, and the fluorides will end up being complete octets so that the charges balance out. So that's basically how that one works. We'll do another one where we have barium. Barium again is got 2 valence electrons. Oxygen has 6 valence electrons. So for simplicity's sake, because I know where things are going to move, we're going to transfer 1 here and 1 here. So the net effect is we end up with barium 2+, and oxygen 2-. So again, we end up with the ions, and we end up with the charges balancing. So we could do this all day long, but we're just going to do it one more time. And I'm going to do it with aluminum. And we're going to have 2 aluminums, so we're going to set up aluminum. And aluminum has 3 valence electrons. And we'll go ahead and do sulfur. And we have 3 sulfurs, and sulfur has 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay, so again, on this one, you're going to have a transfer of electrons. You'll transfer 1 electron here, 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 and 1 electron here. So the net effect is we end up with 2 aluminums that are 3+, and 3 sulfurs that have complete octets, so they're 2-. And so if you're looking back and you're thinking about why aluminum has to have 2 aluminums and 3 sulfides, so when we're done it's Al2S3, it's because that it takes 2 aluminum ions to provide enough electrons to transfer to 3 sulfurs so that the charges will balance. So your total positives equal your total negatives. So that's how we would look at it with respect to Lewis structures, but let's look at what goes on then once we form the ions. Well, for ionic bonds, we have 3 rules. First one is Coulomb's law that states the potential energy between 2 ions is directly proportional to the product of their charges and inversely proportional to the distance of the separation between them. Huh? Okay. This is what you want to look at. So what happens here is as the charges go up, the energy goes up. As the distance between the 2 points goes up, the energy goes down. This is just a ratio. You will not be asked to run this. It is a proportionality because we're actually missing parts. But what we're really looking at is that we're looking at the charges. And notice that we're talking about cations and anions. Because if you put in 2 cations, then you get a repulsion. So you still get the energy, but now the energy is a positive energy, not a negative energy, because a negative energy means that it's favored. Okay. Now the next rule is lattice energy, which is the energy associated with the formation of a crystalline lattice from the gaseous ions. Now, lattice energy is kind of interesting because different people do it different ways. The definition is to form the lattice energy from the gaseous ions. So, simplicity wise, you're going to have pluses and minuses forming a crystal. That being the case, energy is always given off. So, lattice energy written this way is always negative. However, if you flip it and you take the crystal and you separate the ions, then it takes energy, so it's positive. So different places you'll see a different sign on lattice energy depending upon which way they're looking at it. So please don't let that freak you out. More about that later. And then the third thing is the Born-Haber cycle. And this relates lattice energies to ionic compounds, to the parts that go into making it up. Their ionization energies, electron affinities, etc. Now, the Born-Haber cycle is very much like Hess's law. Hess's law stated that you could get the energy of a reaction by looking at the steps that it took to get to the reaction. Well, the Born-Haber cycle is actually doing the exact same thing. So when we look at it, it says cycle because it's kind of one big round thing. So we're going to start down here. So we're going to start here for our overall reaction. And what we're looking at from this step to this step, if we look at the potassium, then we've gone from a solid to a gas. So for the potassium, that's energy of sublimation. So what we have to do is get it to the gaseous forms. Okay, for the chlorine, we're going from the diatomic to the monoatomic. So we're breaking a bond. So that's bond energy. So as we continue up, we've got potassium in the gas form. Remember, chlorine was already in the gas form. So we didn't need to get it in the gas form, but we needed to break it up into the monoatomics. So then if we go from potassium gas to potassium ion, we've ionized it. So that's ionization energy. And we're only losing one electron, so it's first ionization energy. Now, on the other hand, we're gaining an electron, so this is electron affinity. Now, if you notice, all the arrows are heading up. We're gaining energy each time we do that. Now, electron affinity is negative, but for the purposes of looking at where we're going, so at this point in time, we're at our ionic state. And so electron affinity may be negative. So technically, it really should be kind of on the downhill slide. But I just want you to see that these are the steps that it takes to go into it. And then if we start with the ions in gaseous form, and then we go to the crystal, which is solid, then this is lattice energy. So to complete the cycle, this would have been the energy of the reaction overall to get from the elemental states to the final state. So it's one big loop. So what happens is if we look at it, the overall energy is the sum of each of the steps. So if this is delta H sub 1, and this is delta H2, and delta H3, and delta H4, delta H5, and this would be delta H overall. So in this particular case, when you look at it, all the steps that go into it, it doesn't matter if these values are positive or negative. So this electron affinity would have a negative value, but you're still adding it all together. So these are the steps to get us from the elemental state to the crystalline state via all the steps that it takes. So the Born-Haber cycle is a hypothetical multi-step process, and the steps can include, but they may not include all of these. They may include half of them. They may include 2/3 of them, it doesn't matter. If we have a solid or a liquid, it has to go to a gas. If you go to a solid, from a solid to a gas is sublimation. If you go from a liquid to a gas is vaporization. Okay, if you have any diatomic or P4S8, you're going to have to eliminate the bonds. You're going to have to ionize species. So in order to form cations, you use ionization energy. If you need to form anions, it's electron affinity. And you're going to combine the ions to form the salt, which is the lattice energy. So the net effect is all these previous things will sum to give us the overall formation reactions. So if we look at the figure from your text, again, they're starting with the elemental sodium and chloride. The sodium, they're moving to the gas. Then they're going to split up the chlorine. They split it up both ways. They took sodium and ionized it. Electron affinity, we did say, was negative, so they went ahead and put it on the energy scale coming up. I did mine basically to get us to the high point. This would have been my high point here. And the lattice energy here, and again, this is the overall. So again, it's a cycle because basically you have to complete the loop. So how do we do this? So if we're looking at specific reactions, it's much easier. Now, we're going to work the first one through with math. But after that, I'm most concerned not with the math, but with you identifying the steps associated with it. Okay, so here we go. This is our overall reaction we want to see here. So here's our first ionization energy of magnesium. So that would be magnesium to magnesium plus. Here's our second ionization, plus to magnesium 2 plus. The bond energy, so that's taking chlorine and breaking it up. Electron affinity is chlorine plus an electron to give you chlorine minus. And then the lattice energy is going from magnesium 2 plus 2 chloride ions to produce magnesium chloride. So then these would total to the enthalpy of formation. The overall reaction is going to be magnesium solid plus chlorine gas yields magnesium chloride solid, which is your salt. Excuse me. So what you're seeing here is, wait, shouldn't all these add together? Yeah, but we're missing something. We have ionization energy. What we didn't do is energy of sublimation, which is taking magnesium solid to magnesium gas. So that's the one we're missing here in this process. So if we look at it, we're like, okay, that's fine. We've got one magnesium. We're going to gain the electron. Wait a minute. Bond energy splits up the chlorines. But we need 2 of these chlorines. So this would have to be multiplied by 2. And everything else would work. So what we're going to end up with is, and I don't know if that'll have enough room here, so X plus 738 plus 1451 plus 238 plus 2 times negative 348 plus negative 2440 is going to be equal to negative 641. So basically, all these is a simple addition. If it's negative, you add it as a negative. If it's positive, you leave it as a positive. So what ends up happening is the energy of sublimation comes out to be 68 kilojoules per mole. So that would allow us to calculate it. Now, it's all the same series of steps, whether you're calculating it or whether you're not calculating it. So what I'm most concerned about is that you ID the steps. So we're going to set up the following using equations and name each step. There are going to be no numbers. And this lends itself to a ordering problem. You know, give it all these steps, place them in the proper order. Just giving you a hint on that one. Online. Okay, if you are not online, then you would be given a compound and asked to set up the following equations and name each step, etc. Okay, so here we go. So we know that this is going to come from iron and oxygen to produce that. Iron's a solid, oxygen's a gas. I didn't leave myself enough room. So this is going to be 3 halves and this is going to be 2. All right. So what we're going to start with is you can start with iron or you can start with oxygen and you can mix them up. I just find it easier to start with one. So the first thing we have to do is take iron solid, it would have to be 2, to go to 2 iron gases. So this would be the energy of sublimation. Remember, sublimation is to go from a solid to a gas. And you would multiply this by 2 if you were actually doing the math. Then from there, we need, in this compound, iron's going to be 3 plus and oxygen's going to be 2 minus. So what we're going to do is we're going to go from Fe, gas, to Fe plus, gas, plus 1 electron. Again, this would all be multiplied by 2. This is the first ionization energy. And again, multiplied by 2 the whole way down. Okay, the second step would be to take the 1 plus and produce the 2 plus, 1 electron again. You'd multiply by 2. This is the second ionization energy. And if we were just worrying about the steps, we wouldn't worry about the multiplication unless we were doing the numbers. Okay, so then we would have the third one. So we're going to start with the 2 plus and go to the 3 plus. This would be the third ionization energy. And remember, you can abbreviate it or write it all out, times 2. So that gets us to iron where we need it to be. I didn't put these in as gases, but they are gases. Once we got it to gas, I'm kind of okay with it. So now we're going to take 3 halves, O2, which is already a gas, so we don't need to sublimate it to 2 O gases. So this would be the energy of the bond. So it's bond energy, and it'd be multiplied by 3 halves. So then we take our oxygen, and we would gain 1 electron, and we would find O1 minus, so that's electron affinity number 1. And again, we'd have to multiply that by 3 halves. And then we take the O1 minus, and we gain another electron, which would take us to O2 minus, which is our electron affinity number 2, or second electron affinity. Again, we multiply that by 3 halves. So at this point in time, I cheated and didn't write the gases in here. So if I'm multiplying this by 3 halves and this one by 3 halves, then at this point, actually, this would be multiplied by 3, not 3 halves here, because we took and got the 3 halves out here. So this one actually is just 3, and this one would be 3. So this one is 3 and 3. So the net effect is we got rid of the 2 because of the O2. So then at this point in time, we combine them, so we're left with the 3 Fe, 2 pluses, no, 2. Got my charges mixed up. 3 pluses plus 3 O2 minuses, gas, yields, and I messed it up several places, so let me just reline it up. So if you'll notice, what I've been trying to do is keep the arrows lined up. I've done a okay job. It's not great. 3 plus gas plus 3 O2 minus gas yields Fe2O3 solid. So this is my lattice energy. So then, if you go back up here, and I'm going to use a light blue here, and cancel what we have. So we have 2 here, 2 here. We end up with 2 here, 2 here, 2 here, 2 here. We're left with 2 there. The electrons, we've got 2, 4, 6 electrons, and we've got 3 times 1, so we have 6 electrons here, so all electrons cancel. We're left with 3 times 2, which is 3 O's. So there's my 3 O's. There's my 3 negative 1s. So I'm left there. Okay, so if we go back up here and look at it, we have our F3 plus, and F3 plus, our 3O2, our 3O2. So we're back to where we were. So if we write what we're left with 2 Fe solids plus 3 halves O2 gases yields Fe2O3S, which is the overall energy of reaction. So if you look at this step, it's just a series of steps, and it's a series of taking it apart and putting it back together in such a way that you start with what you have elementally and get to the ions that you need. And again, it should close the loop. If things don't cancel, then you've done something wrong. Online or in person, you may be asked to write this, or you may be given something like this with boxes missing, and you have to identify the missing parts. Can you do it with the math? Yeah, but if you can do this part, you can do the math. So I don't worry about the math so much, because the math is really easy based upon this. So you'll be good to go on that one. So let's talk about other trends in lattice energy. As the size increases, and we're talking about the ionic compounds involved in the lattice energy, the lattice energy itself gets smaller. Okay, so we're not talking about the charges. We're actually talking about the size, because when we're talking about size, the size is really the R, the distance in between the two nuclei. So basically, if you're looking at it, because remember, lattice energy tends to be negative, so it's more positive. Whoops. Okay, that means it's a smaller absolute value. So if you're looking at these values, as you go up here to cesium chloride, lithium is the smallest, the chlorides are all the same. So we're looking at lithium, sodium chloride, potassium. So as the ion size gets larger, your R value gets larger, so therefore your energy drops. And as the ionic radii gets bigger, because remember, it's going to get larger as it goes down the table, again, your absolute values get smaller. Always look at absolute values because, as I said, some tables give you lattice energy that's positive and some gives you lattice energy that's negative. And remember, the negative means that the energy is given off when the ions snap together. So here are some trends in lattice energy. Remember, we said as the charge increases, we were doing size before, but as the charge increases, the lattice energy gets larger, which makes perfect sense because remember, the Q1, Q anion, Q cation were on the top, and it gets more negative, which gives it a larger absolute value. So if you look at it, if you're looking at lithium with the same cation, different anions, then you have the trend we just saw. But if you come over here and you look at different ones, so for example, if you look at your periodic table, magnesium and sodium are on the same group. So where's sodium chloride? Okay, so you're comparing, the chlorides are the same here. Notice that the energy gets tremendously larger once you've got a larger charge. So calcium and potassium are the same. So wait, they've got strontium. Why did they do strontium? So strontium is much larger. So strontium is the same as rubidium. So this is strontium chloride. Do they have rubidium chloride? They didn't put rubidium chloride in here. Okay, so these are all charges. Remember, scandium is 3 plus, nitride is 2 minus. So this is 2 plus and 2 minus. These are 2 plus and 1 minus. So notice as you go, basically 2 times 1 versus 2 times 2 versus 3 times 3, the lattice energy gets much larger. So this is kind of interesting in terms of the trends and looking at how the trends are observed. Okay, now closer look, calculation of lattice energies, the Born-Haber cycle. This one's actually cool. If you're into history or into World War II and I, you might want to read through this one because it kind of looks really, really boring. But it's actually very, very interesting in terms of the historical record, etc. So if you like history, especially World War One, World War II, you might want to look at this because the Born-Haber cycle had a tremendous impact on the wars, which keep in mind that there are things in history that we need to look at because they had a massive effect on what happened afterwards. So history's not all good, history's not all bad, but if you look at different contributions within the scientific community at different points in history, it can be very interesting, educational, and edifying. So got words in there. Okay.